Welcome again to our Chemistry Matters series. I'm your host, Francine Taylor Campbell. Today we are exploring the atom. Now let's look at the syllabus objectives from our CSEC chemistry syllabus. We should be able to describe with illustrations the structure of atoms of atomic number 1 to 20, state the properties of the subatomic particles, electrons, protons, and neutrons, define atomic number and mass number, interpret the notations of the form given shown on your screen, and define isotopy. So these are our guiding questions for this episode. What are the building blocks of matter? What makes up the structure of the atom? How can these subatomic particles be differentiated? And how are isotopes formed? So let's check what you remember about the atom. So in the last lesson, we looked at the fact that matter can be broken down into basically the what we call the subdivisions, the smallest part of matter. That would represent atoms. So atoms essentially are the building blocks of matter. And when we think of the particles of matter, they can represent atoms, they can represent ions, and they can also represent molecules. Each element that exists would be made up of the different atoms of that element. And each atom of that element would consist of 3 subatomic particles. And this is what we will be exploring today. So, how could we represent the atom? Let's see. What you will need for this particular exercise, if you can look at what we have here, we have styrofoam plate, some representations of the different atomic particles, subatomic particles, and we're using seeds. But just consider this. Do you remember what the solar system looks like? All right, yes. So you would have learned about solar system in primary school, right? And we know in our solar system, as shown on our screen, we have the center of that solar system, which is the sun, yes? And orbiting the sun, we have the planets. So we're going to be basically using that model, and that was in the first place how scientists viewed models of the atoms, somewhat like the solar system. And we're going to basically use that particular analogy, right? So in the center of our atom, let's look at what we have here. We have the nucleus, right? That is in that central portion there, right? And so there are some particles that we'll place in the center. So make sure you have all of the materials that you need. If you don't have these seeds and beans and so on, you could also use sweets, right? Colored candies. Make sure you have a marker. We would have already created our circles, right, with our marker. And if you don't have Play-Doh, this is what I've used here. You could also use certain wires or cords. All right, so what will we do with these? So if you look at the diagram, you would realize that in the center of the atom, which is the nucleus, so this is my Play-Doh, which is going to represent my nucleus, right in the center there, yes? In the center, we place the protons and the neutrons. And what we know about protons and neutrons is that they're of similar mass. And so you can get materials that are similar in mass. So I have some grains of corn, and we're building here the carbon atom. So in the carbon atom, we have 6 protons, right? And so here I have my protons. 2, 3, 4, 5, and 6. All right? and we have 6 neutrons. So I'm using my gongo peas here to represent my neutrons. So I have 6 neutrons. Now it doesn't always work that the number of protons and neutrons are equal, but in carbon they happen to be equal. So I again would put in my 6 neutrons. As I said, when you're choosing particles for this, you can get those that are of relative similarity in mass and size. So we have 6 protons, 6 neutrons, that's for carbon. And on the energy levels, we represent those using shells at this level, right? We have our electrons. When choosing materials for your electrons, you want to choose something that is much smaller than your protons and your neutrons, and I'll explain why in a couple of minutes. So again, carbon also has 6 electrons, all right? And how they are placed in the first shell, that shell can only hold 2. In the next lesson, we will explore this a bit more, but for now, we're just representing. So we have our 2 electrons in the first shell, and of course, since it has 6, then we should have 4 more left, and those 4 would go into the second shell. All right, oh, there goes my electron. All right, good thing we have some more. So we'll put our 4 electrons, and notice I am spacing them, and we'll tell you why we have to space them in a little while around my shells. So this is very simple, a model of the atom. So again, this is representing carbon atom. We have 6 protons, 6 neutrons, that is in their nucleus. So our protons and neutrons are in the nucleus, and our electrons, also 6 electrons, are placed in the energy levels, and these are represented here by our shells. So how do these particles, or how does this model explain the structure of the atom? As stated, the atom has a central portion, right? And that portion is positively charged. Where does it get that charge from? It's positively charged because the protons are positively charged. So in our atom, protons are positively charged. Neutrons then have no charge. But the positive charge must be balanced by the negative charge of the electrons. And so orbiting the nucleus, so they're not stationary, they are constantly moving, we would have our electrons. All right. Now, if you look at our table, we will see that there is a representation of the mass of the atom, the mass of the proton and neutron, as well as the electron, right? And if we look at those properties, I mentioned some of the properties earlier, right? We would have to check now, how does this affect the atom, right? And in chemistry, we use a term called relative mass. Why do we say the relative mass? So on the table that you're seeing, we see that the relative mass of the proton is shown to be 1. That of the neutron, the relative mass is 1. And we have here the relative mass of the electron is given as 0. Why would we give it a relative mass of 0? All right, we will explain that. And as well, you will see that the charge on the proton is given as positive charge, and that on the neutron, no charge, and on the electron, it is negative charge. All right, so we do not use the actual mass because the actual mass of a proton or a neutron is of the order of 10 to the minus 27 kilograms. Now, if you look at the screen, you can imagine that it is 0.0, well, we actually have about 26 zeros 0.00000000167, right? That is how small it is. Now, we really can't work with that in certain calculations because that is too small, right? And so when we compare both the protons and the neutrons, then we find that their mass is similar. And so since it is similar, then we basically have a ratio. The ratio of their masses is really about 1 to 1. So we use the term relative mass, and that's where we get a relative mass of 1. And then the electron, by comparison, as I mentioned before, you want to represent it with some very tiny seeds, right? Because the electron is 1 over 1840. That is how small it is compared to the proton or the neutron, right? And basically, if you should divide that again, then it means, therefore, that the mass of the electron is so tiny that we say it is negligible. And that is why on the table, sometimes it is given a mass of, a relative mass of 0. I hope we're understanding so far. Now, how do these particles affect the atom? All right? So, obviously, as stated, the charges, we have positive charge in the center, in the nucleus, negative charges on the orbiting the nucleus, all right? And so essentially, the charges, positive and negative charges, will cancel to give the atom, to make the atom neutral, right? So the atom would be neutral because of the canceling of the positives and the negative charges, right? In addition to that, as stated, since electrons, their mass is really negligible, then it means that the actual mass of the atom is coming from the nucleus. And so how do we represent that now on our periodic table? We use what is called the standard atomic notation. So, in your standard atomic notation, you find that the mass of the atom is recorded as a number at the top, and we will come back to this. And the atomic number, which represents the number of protons, is the number that is shown at the bottom. But before we go any further, let's do a quick check. Let's see what you have grasped so far. So our first question, what contributes to the mass of the atom? I'm sure I just mentioned that. Think about it. What makes up the mass of the atom? I hope you mentioned protons and neutrons, because as was stated, that mass is coming from the nucleus. All right? Because our electrons, the mass of the electrons is really negligible. All right, last question in this section. Why are atoms neutral? Again, I hope you were paying attention. The atom is neutral because, yes, the protons, which are positively charged, will cancel out with the electrons that are negatively charged. And so overall, the atom is neutral. Beautiful. All right, so let's continue. So as we were mentioning earlier, the standard atomic notation give us information about the particles in the atom. So if you look at your periodic table as shown on the screen, you will see that there's a number at the top of each element, the symbol on the periodic table. So say for instance, we're looking at helium, which is He, that is in the final group or column in the periodic table, right? You will see that it has a number at the top, which is 4, and another number at the bottom, which is 2. So the number at the top represents what we call the mass number, and the number at the bottom represents the atomic number. So we're going to get into some calculations, right? We want you to try this. So on your screen, you will see helium, 4, and 2 at the bottom. So let me show this on my whiteboard. All right, I hope you are ready for this. So we have helium, use the black. So you would see something looking like that. Nowadays, you may have periodic tables that may give you the atomic number at the top in terms of locating the element, but when we're writing the standard notation, this is how we represent it, right? So this is representing the element helium, right? And there's a number at the top, which is always larger. This is called the mass number, all right? So this is our gone. This is our mass number. And the number at the bottom represents what we call our atomic number. All right? Now, once we are given these numbers, we can calculate the number of each subatomic particle, right? Once we have this information, how can I know the number of protons? Essentially, the atomic number represents the number of protons. So once I see this atomic number that does not change, that represents the number of protons. And the mass number, remember we said the mass of the atom is coming from which two particles? The protons and the neutrons. And so the mass number would represent the number of protons and neutrons. So, therefore, look at this. What do we notice here? So I can work out the number of protons for helium. What's the number of protons? In this case, it is 2. And if the mass number is number of protons plus neutrons, then to get the number of neutrons, what do I do? Come on, you are able to do this. Number of neutrons is going to be the mass and I'm subtracting the number of protons. So luckily in this case it works out to be 4 minus 2. So the number of neutrons is equal to 2, right? Good. So for our element here, helium, we have 2 protons, 2 neutrons. So how do we work out the number of electrons? What did we say earlier? What makes an atom neutral? The atom is neutral because the protons, number of protons and the number of electrons are equal. And so, if we know the number of protons, once it's a neutral atom, then the number of electrons is going to be equal to the number of protons, right? And hence that number is 2. Great. So, of course, we will now want you to try some for yourselves. So, let's look at these examples here, right? I'm going to have you try boron as shown on your screen, right? The mass number is 11 and the atomic number is 5. So using the same methodology that we used earlier, I want you to try to work out the number of protons, electrons, and neutrons that are in boron. All right? And after we have done that, we'll try one more, and we will do that for chlorine. Okay? And as you can see on our screen, the atomic and mass numbers are also given. So, boron. Have you worked out boron? So, let's write the standard atomic notation for boron. So, boron should be written as shown here. All right, based on what we just learned, how many protons, how many electrons, how many neutrons can be found in boron? All right, so let's see. Are we ready? So again, identify our atomic number and our mass number. All right? So, how many protons are in boron? From what we saw earlier, atomic number is equal to the number of protons, and hence that is equal to 5. Now remember, the mass number is the number of protons plus neutrons. So how many neutrons are in boron? How do we calculate that? That is going to be equal to 11 minus 5, which gives us 6. So again, notice in this case, the protons and neutrons are not the same in terms of number. All right? And then electrons, in a neutral atom, the electrons equal to the number of protons, right? So, what's the number of electrons? Also 5. Good job. All right, last one. I asked you to also look at chlorine, right? Again, if you look at your screen, you will see that the notation for chlorine, and notice the first letter is capital when we're writing symbols. The second letter would be a common letter. All right, so for chlorine, we can see on our periodic table 35 and 17, right? Okay, so again, we want to identify the atomic number and the mass number. Good? Okay, so what's the number of protons? You should by now get the hang of it, right? Yes? Number of protons, same as the atomic number. Yes. Number of neutrons. We're subtracting. What are we subtracting? 35 minus 17. And that should give us 18, right? And then finally, number of electrons, same as our protons, once it is a neutral atom, and that is going to give us 17. So, I would encourage you to continue practicing how to work out the number of subatomic particles in any atom, right, of an element. All right, so let's continue. Now, I want you to look at your screen, and you will see the representation of atoms of oxygen. And you will see that there's something that looks interesting. I won't use the word strange. Look at our screen. What do you notice about the oxygen atoms represented? We notice that we have them having the same bottom number, and the mass number, we have a mass number of 16 on one, 17, and 18. So, what is happening here? What do we call this representation? All right, so let's look again. What is similar about these three atoms? They have the same atomic number, because we just learned that that number at the bottom is the atomic number. And then, what happens to the number at the top? We see that that is changing. Right. So they have the different mass number. So, essentially then, the atoms represented would be the same element because an element is defined by its atomic number. So it has the same element, which is oxygen, and it has the atomic number of 8. But the mass number is different. And since the mass number is different, it means that what makes up the mass number again? If it has the same atomic number, what else makes up the mass number? The number of protons. So it means that in these atoms that we have represented, they have different number of neutrons. There's a special name for this particular representation of our atoms. They are called isotopes. Yes. So how are isotopes formed, or what are isotopes? If we look at our example shown, it means therefore that isotopes would represent atoms of the same element, yes, same oxygen, with the same atomic number. That means it has the same number of, yes, you guessed it, protons, but it has a different mass number, as we can see, yes. So that means it has a different number of neutrons. And isotopes are generally quite useful, especially those that are unstable. So we have what is called radioisotopes or radioactive isotopes. Now, what are these and how are they formed? Or how are they used, sorry. So radioisotopes or radioactive isotopes are those isotopes formed where the nuclei, that central part of the atom, is unstable, and so it will basically split to release radiation. So I'm sure once you hear of that, you're thinking of, uranium and others that we know will emit a lot of radiation, and it may be what we call dangerous. But there is actually use for these radioisotopes. What are they used for? So they're certainly very useful in medicine and in industry, and some uses are shown here. So for instance, in the treatment of cancer cells, we know of the use of cobalt-60. Yes. Iodine-131, useful in the treatment of thyroid, right? Defective thyroid glands. They are really used as tracers. And we must have heard of dating those fossils, remains of plants and animals for millions of years ago, the use of carbon-14. And to generate energy, we know of the use of uranium-230, is that 5 or 8? 235, all right? So these are quite useful. All right, so we're almost at the end, but let's check what you have learned. What did you learn today? Today we learned that, of course, atoms consist of 3 subatomic particles. We know them to be protons, positively charged, neutrons having no charge, and electrons that are negatively charged. Protons and neutrons are found in the nucleus, whereas electrons can be found orbiting the nucleus, right? Yes? And for a neutral atom, we know that the number of protons and electrons are equal. What else did we find out? Yes, we found out that the number at the top of our atomic notation represents the mass number, and at the bottom we have our atomic number. Yes. And from that information, we can calculate the number of subatomic particles. And finally, we learned about isotopes. Yes. How are they formed? Or how do we define them? Isotopes are formed because we have atoms of the same element having same atomic number, that's number of protons, but a different mass number, which is the number of neutrons. And therefore, Isotopes will have the same chemical properties, yes, but different physical properties. And finally, we know that some of these isotopes, called radioisotopes or radioactive isotopes, are useful in medicine and in industry. So there you have it. We are at the end of this particular lesson. So that's it for today. We will see you again next week when we'll be exploring some other fundamental chemistry concept that is needed to successfully complete your CSEC examinations. See you next time.